Okay, a uranium-238 isotope which has a half-life of 4.47 exponent 9 years decays by emitting alpha particles into thorium-234 nucleus. Calculate the decay constant and then the rest. Okay, first of all, we look at this. This one is uranium-238. Maybe we should write out the element first. Uranium-238. It decays become thorium-234 or thorium-234. Hold on a second. Okay, thorium-234. Okay, now this is the element. Yeah. Half-life. Okay, we have a half-life. Okay, but in unit years. So be careful with all these units in years. Okay, decays by emitting alpha particles. So this is alpha decay. Remember about alpha decay. That means if one nuclei decay, right, if one nuclei decay, one nuclei decay, that means if one nuclei decay, it will emit one alpha. Alpha is helium 24. Yeah, helium 24. One nuclei decay means emits one alpha. Now remember this. Okay, emits alpha particle into thorium. Okay, alpha particle is helium 24. Okay, maybe I should write it down. Put it down here. Yeah, be better. Then yeah, this should be better. Yeah, alpha decay. Alpha decay, that means one nuclei decay emit one alpha. One nuclei decay emit one alpha. Okay, so let's move on. Find the decay constant. Find the decay constant, which is lambda. Okay, lambda. As I said, once you have half-life, actually you can find decay constant. Yeah, once you have half-life, you surely can find decay constant. So next, so let's do question A first. Question A. Okay, I have the half-life of 4.47 exponent 9 years. So I need to change to SI unit first lah. Always make sure change to SI unit first. So I know that in 1 year you have 365 days, and 1 days you have 24 hours, and 1 hour you have 60 minutes, and 1 minute you have 60 seconds. Understand? 1 year has 365 days, 365 days. Yeah, 365 days, and 1 day you have 24 hours, 60 minutes, and 60 seconds. Okay, so I just multiply this with this lah. Okay, so I just 4.47 exponent 9 years. So I multiply with all this. Yep. So I want to change to second. Understand? I want to change to second. So let's calculate 4.47 exponent 9 multiplied by 365 days, multiplied by 24 hours, multiplied by 60 minutes and 60 seconds. So I got my half-life is actually 1.40966 40966, yeah, 966 exponent 17 Second, I got my half-life in SI unit. So now I can find my decay constant also in SI unit, which is the formula is ln 2 over half-life. Lambda half-life is ln 2 over lambda. So the other way around is lambda is ln 2 over half-life. Okay, lambda is ln 2 over half-life. Okay, so let's calculate. Yeah, let's calculate ln 2 over half-life. Yeah, ln 2 over half-life, which is 1.40966 exponent 17 second. That's my half-life. Now calculate. Yeah, ln 2 and then divide by this 1.40966 exponent 17. 1.40966 exponent 17. Okay, so my lambda is 4.92 exponent negative 18 per second. So that's my lambda decay constant. Understand? I got my answer. All right. So the unit is per second lah. Yeah. So B, what is the mass of uranium-238 required to decay with activity this one, becquerel? We know that becquerel is we know that 1 becquerel is 1 decay per second. So becquerel means per second. Understand? Okay, mass. You want to find mass, yeah? Mass. This is the considered the total mass lah. Total mass required to decay with activity. This is the activity. Activity is actually also the decay rate, dN over dt. dN over dt. Okay, write down the information first. So we have okay, just want to put this over. This one is just put it over here. Okay, rearrange my stuff. Okay, this one, the whole thing, just want to adjust to here. Okay, now adjust my stuff a bit. Okay, so question B. Question B. I have the decay rate, activity or decay rate dN over dt with 2.22. Okay, this one you need to put negative, because the amount is decreasing. Negative means amount is decreasing. 2.22 exponent 5 per second becquerel, or you can write as per second lah. It's already SI unit. Yeah, so the negative here, it means the unstable nuclei or radioactive nuclei is decreasing. Yeah, it means the negative means the amount is decreasing. Okay, you must put a negative sign, although here don't negative sign. Here you must put a negative sign. Okay, so we can want to find mass. Of course, we can do the previous example. He give you the dN dt, the decay rate, and ask you to and also the mass. Ask you to find the lambda. You see that? And now is also use this formula. Understand? Also use this formula. With the dt and the mass. Okay, so we can use the same formula, which is this one lah. dN dt equal to negative lambda n. Understand? So we can use this formula. A equal to negative lambda n, or you can write it as dN over dt negative, dN over dt negative lambda n. So I can find my number of nuclei first. Number of nuclei for this uranium. Then from number of nuclei, I can find the mass. See that? So, okay, let's continue. Remember, the density or activity always come with negative sign. Always come with negative sign. Don't put a positive sign there. Yeah? So, it is 2.22. 2.22. Wait, what is 2.22? Okay, 2.22 exponent 5. Is it exponent 5? Exponent 5. This one is per second, or becquerel is per second lah. Okay, equals to okay, just want to change it. Per second, and then negative lambda. My lambda is this one. You see that? 4.92. Okay, 4.92 exponent negative 18. This one also per second. And then n, I can find my n. So then only you get negative, negative, positive. And then you get negative, negative, positive. And then we divide and see how many number of nuclei here. Negative, negative, positive. So 2.22 exponent 5. 2.22 exponent 5 divide by 4.92. 4.92 exponent negative 18. Negative 18. Okay, 4.92 exponent negative 18. So the nuclei is 4.5122. 4.5122. Yeah, exponent 22. Exponent 22. Unstable nuclei. Okay. Which is what? Which one is the unstable nuclei? The uranium 238. The uranium 238. Understand? This one is just want to put it over here. Uranium is unstable or radioactive. Unstable or radioactive. Whereas radioactive, whereas the thorium is a stable nuclei. Thorium is stable nuclei. Uranium is unstable radioactive nuclei. So I have this amount of uranium. See that? Total molecules, total nuclei. So I can find the mass. I have the n. I can find the mass. I also have the molar mass. You see, he said uranium 238. That is the molar mass. I got the molar mass also. Yeah, the molar mass. This 238. This is the mass number. It is also the molar mass. You understand? It is also the molar mass, but in gram per mole. The unit gram per mole. So I can say the molar mass of uranium is 238 gram per mole. So I need to change to kilogram. I must change to SI unit. SI unit. So it becomes what? It becomes 0.238 kilogram per mole. Divide by 1000, 0.238 kilogram per mole. So I have the molar mass also. Molar mass, this mass number is the nucleon number. Nucleon number is also the molar mass. So I have the molar mass, I have the total molecule. So what do I do now? First I find the number of mole. First I find the number of mole. I use the Avogadro constant. I have the Avogadro constant, which is also Avogadro constant. You can find from where? Avogadro constant you can get from the list of constant. List of constant 6.02 exponent 23 mole. Number of nuclei per mole. So 6.02 exponent 23 nuclei per mole. Understand? 60223. 60223. So I can find the number of mole. Number of mole is the total nuclei divided by, total nuclei divided by Avogadro constant, which is 4.5122 exponent 22, and then divide by Avogadro constant 6.02 exponent 23. Okay, so I can find the number of mole. 4.5122 exponent 22. Wait, okay. Exponent 4.5122, 4.5122. 4.5122 exponent 22 divide by the Avogadro constant 6.02 exponent 23. Exponent 23. Okay, I got the number of mole. Which is 0.07495. 0.7495 mole. So this total molecules has this amount of mole. So I got the number of mole. I also have the molar mass. I can find the total mass for this total molecules. So from here I can get the total mass. The total mass is the number of mole multiplied by molar mass. See that? Number of mole. Okay, this one I actually come from the formula. Number of mole is total mass divided by molar mass, isn't it? Total mass divided by molar mass, get the number of mole. So once I multiply this to the top, molar mass, I multiply with number of mole, I get the total mass. So the total mass is the number of mole multiplied by molar mass. So I get the total mass. Very simple, isn't it? So the number of mole 0.07495 mole multiplied by the molar mass, multiplied by molar mass of what? Of molar mass 0.238 kilogram per mole. Number of mole multiplied by molar mass. Then I can get the total mass. Okay, so 0.7495 multiplied by 0.238 kilogram per mole. So I got the total mass, which is 0.0178 kilogram. That's the total mass of uranium-238 unstable nuclei. So this is the total mass of uranium-238 required to decay with that activity. Understand? With that activity. So that's it for question B. I hope you understand the concept, the way to do it. Okay, so now question C. What is the number of alpha particles per second for the decay of 30 gram? So this is so long. This question is so long. Okay. So question C. Question C. Let's do the question C. So he said, now I have the mass, number of alpha particle per second. That is actually the decay rate. As I said, one alpha decay is this one lah. Again, want to write it over here. Alpha decay. So one nuclear decay means emit one alpha particle. So number of alpha particle emitted per second, that means the number of decay per second. Understand? So this is also, in other words, he wants you to find the number of decay per second. Understand? Which is the decay rate, dNdt. He wants you to find the dNdt. Number of alpha particle emitted per second is the number of nuclei of unstable nuclei decay per second, or number of uranium-238 decay per second. So this is actually dNdt, or is also called activity. The answer should be negative. Yeah. So he want to find dNdt. So for this 30 gram, 30 gram is the new total mass. This is the total mass. Understand? So I have to find, that means I have to find the number of nuclei for this total mass again. So a long, very long question. So that means I have to do the whole thing again. Never mind, I can do it. Yeah. So so now the total mass is 30 gram. 30 gram. So I need to convert to SI unit lah. Always convert to SI unit first. Yeah, 30 gram is how many kilogram? So divide by 1000. Divide by 1000 is 0.03 kilogram. Okay? 0.03. Divide by 1000, 0.03 kilogram. So I need to find number of mole first, because I already have the molar mass. Okay? Uranium-238 also. Yeah, uranium-238. This is still about uranium. This is still about uranium-238. And then from the 238, that one, you know the molar mass. The molar mass, okay, I write it over here again. So the molar mass is again 238 gram per mole, which is also 0.238 kilogram per mole. Okay, you already found just now, yeah, 0.238 kilogram per mole. Okay, in SI unit. So I have the molar mass, I have the total mass, so I can find the number of mole using this one. Understand? Using this one. Okay, so right over here. Yeah. So find the number of mole first. Find the number of mole. Okay, find the number of mole. So my total mass is 30 gram just now, or 0.03 kilogram. So I divide by 0.238 kilogram per mole. So I can get the number of mole. The total mass divided by molar mass. Total mass divided by molar mass, I get the number of mole. 0.03 kilogram divided by 0.238 kilogram per mole. So I get the I got the number of mole is 0.12605 mole. Maintain as many decimal places as possible so that more accurate. 12605 mole. Okay, so I got the number of mole. I can find my number of molecule. I just multiply the number of mole with Avogadro constant. Yeah, just now from this one. Okay, from this one, so this one. That means this one becomes what? To find the total molecules is number of mole multiplied by Avogadro constant. Avogadro constant you can find from the list of constant. Avogadro constant 6.02 exponent 23. Okay, so number of mole 0.12605 mole multiplied by Avogadro constant 6.02 exponent 23. Okay. Okay, so what's the answer? 0.12605 multiplied by 6.02 exponent 23. So the answer is 6.02 exponent 23. So the answer is 7.588 exponent 22 nuclei, or can say uranium-238 nuclei. Okay, so get this amount of nuclei. Yeah, this is the amount of radioactive nuclei for this 30 gram uranium-238. Understand? In this 30 gram uranium-238, this total mass 30 gram, I have this amount of nuclei, this amount of uranium-238 nuclei. And so I got the N already. So can I find the decay rate? Can I find the decay rate, dNdt, the number of alpha particle emitted per second? Yeah, I can find. Yeah, because I also have the lambda already. Yeah, so I use the decay law. dNdt negative lambda n. So I can find my dNdt okay, equal to negative lambda n. So okay, I need to find dNdt, isn't it? dNdt, yes, surely. So it is negative. What's my lambda again? My lambda is what's my lambda? My lambda is 4 point. So just copy this one. Yeah, over here. So it is this one. Okay, that's the decay rate, and that's the decay rate, and then n is this one. 6 point this one. Okay, put it over here. Okay, so that's my end, my nuclei. So and then multiply and see what you get. 7.58821 exponent 22 multiplied by the this negative 4.92 exponent negative 18. 4.92 exponent negative 18. So what I get? Yeah, this is the answer. So it is the decay rate is negative 3.73 exponent 35 exponent 5 per second. So what does it mean? So what does it mean by the negative sign here? The negative sign means it is the amount of decreasing. It means the uranium is decreasing. Uranium-238 is decreasing. The amount is decreasing. So it also means in 1 second. So in 1 second, 3.73 exponent 5 uranium-238, the unstable nuclei decay. Understand? Decay. It also means in 1 second it emits 3.73 exponent 5 alpha particle, alpha helium-24 particle. Yeah, it emits this alpha particle. Understand? So this is what it means. In 1 second, there are this amount of uranium decay, and we know that one decay. We know about one decay will emit 1 alpha. Yeah, based on the formula, you know. Do I write the formula? Yeah, maybe it's like this. In maybe the formula is like this lah. The formula is like this: uranium-238 decay to become thorium-234 plus alpha plus energy. So that means one unstable nuclei decay, and that means will emit will form one stable thorium, and also emit one alpha particle. Understand? So one unstable nuclei decay will emit 1 alpha. So one unstable nuclei decay will emit one unstable nuclei decay will emit 1 alpha. Understand? So this is what it means by decay rate. You also can write this decay rate as activity. Yeah, it's the same. Okay, so that's all for this question. I hope you understand. Okay, the concept of these questions. Okay, that's all. Okay, bye bye.